All right. Hello, everyone. Welcome to the third session of our fall 2024 program for the Virtual Inter-University Symposium on Infrastructure Management. For those who may be new to VISIM, it is a virtual symposium hosted by Professor Pablo Durango-Cohen here at Northwestern University. Today, Hossein and I will be presenting our work as two separate presentations. Each presentation should be about 20 minutes long, after which we will take questions from the audience. Feel free to speak your questions or send them using the chat feature. And as I have mentioned, the meeting is being recorded and will be made available shortly after. Thank you, everybody, for attending. And now to give a little background on Hossein. Hossein is a doctoral candidate at the Chair of Infrastructure Management at ETH Zurich. His scientific work focuses on modeling, assessing, and enhancing the resilience of transportation systems to climate change risks. His research specializes in developing stress testing methodologies as diagnostic practical tools to guide efforts on improving climate resilience. His work contributes to developing strategies for climate adaptation and more resilient infrastructure planning, helping policymakers and operators better prepare for and respond to disruptions. Hossein, thank you for joining, and please take it away.
Thanks, Cal, for the introduction. I'm going to share my screen. Hopefully everything works out well. Okay. So do you see my screen?
Yes.
Okay, good. So thanks again for organizing the event. And I would be very happy to talk today about one piece of my work on stress testing, a practical guide tool basically for climate resilience. Uh, in the beginning, I need to mention that part of the work was in collaboration with the United Nations group of experts, and that work ended up as a United Nations report, which you can find it here, the stress test framework for evaluating the resilience of transport systems. So today, I would like to start first with the difference between risk assessment and stress testing, how they are different than the methodology that we're proposing, and then how we do stress tests using simulations, the case study that we applied our methodology to, and some concluding remarks in the end. So let's just start with some definitions. First of all, transport systems. By the word system, when I refer to system, I mean a combination of these three things, the assets and network, which sometimes they are referred to transport network, the organization that is responsible for managing that network, and also the environment that the network is embedded in that environment, including the users and also the physical environment, all the landscapes, the topography, and also everything like the discharges, the river, and everything like that, which also causes the hazards, and also the organizational environment that all other organizations that the responsible authority for the transport system interacts with. And then it comes to the definition that we agreed on at the group of experts at the United Nations for stress test, and it is defined as one or more hypothetical scenarios designed to help determine if a transport system can continue to provide an acceptable level of service when subjected to one or more potentially disruptive events. And those hypothetical scenarios, they essentially represent situations because of situations where one uncertainty in the system because of a stressor is having significantly more unfavorable values than expected. For example, we have more rainfall in the future because of climate change as a stressor than we previously had, or we will have more traffic on the roads in the future because of change in the mobility patterns or a population growth. So something in our system is performing worse than what we thought or what we designed for or what we planned. That is basically the definition of a stress test. So how it is different from risk assessment is that for to do stress tests, we need to have a reference risk assessment. As we all know, we define some input variables, for example, the intensity of the hazard, travel demand, fragility of our assets, and all those sorts of variables. Then we have a model that connects that basically based on the input variables, it predicts the outputs. And outputs are things like repair costs, number of injuries, and any sort of consequence metric. And the model here could be a mathematical model, simulation model, or even expert's opinion. So they're given some scenarios of input, and then they predict the output. And then based on the output, we measure risks, and we say if the system is doing all right or not. The stress testing, then it's a complementary approach to this reference assessment. And as I mentioned earlier, it is scenarios. It contains scenarios that are worse than the reference case. So we have, for example, more rainfall or more intense rainfall or more traffic and higher number of vehicles on the roads, for example. And then with the same model, we predict the outputs expectedly. They're going to increase. And then we evaluate whether this increase is acceptable or not. So if I want to show the same concept in a more probabilistic way, let's say, so we have random variables representing our input variables. Each one of them has the probability distribution, and then we have a model, and then we generate multiple scenarios, and then we end up having the probability distribution for the outputs. And then based on the probability distribution of the output, we calculate risks. And again, we say whether it is okay or not. The same case for stress testing, though this time the probability distribution of the inputs are different, and they are different in a way that it would generate more unfavorable or worse situations. As you can see, for example, here we have more intense hazards or we have more traffic demand. And as a result, we have more repair costs. We have higher repair costs and higher number of injuries. And then again, we evaluate whether this increase is okay or not. A very quick note on risk assessment versus the stress test assessment. For risk assessment, we have a risk measure. For example, in this case, is a percentile of the repair costs. And then we have a limit. And we say, for example, the probability of having repair costs more than a certain amount should be less than 5%. And the same case is also for stress testing. We have new limits and new exceedance probability, for example. And then we measure whether this increase in risks is okay or not, considering these thresholds. There could be other ways of assessing. It could be, for example, mean value of the total costs, or median, or any other percentage, or things like this. But the concept is more or less the same. So to start with the methodology, so that is mostly basically taken from this paper of mine that was recently published on simulation-based stress tests. So we applied that methodology to the case study. But before talking about the methodology, I would like to give a quick overview of the case study, which is the road network in the eastern part of Switzerland in the region of Chur. And it is, if I use my laser pointer, so the region is where the Rhine River is located. There are two streams of the Rhine, one upper Rhine and one lower Rhine. They merge at this point, and then they form the Rhine River. And historically, there have been scenarios of flooding in this area. And also, this city is surrounded by mountains and slopes, and there are also landslides because of heavy rainfall in that region. And some historic events are also mentioned here. And our concern is the transport system, the road network in that area, which is composed of 51 kilometers of national highways, around 31% of all national highways in the canton or the province. 5 554 kilometers of other types of roads, 121 bridges, and of them, 18 of those bridges are actually on the Rhine River, so they're susceptible to scouring. So the concern for us is to evaluate risks with respect to extreme scenarios of rainfall that lead to flooding and landslides, and then a stress test our system with some other scenarios that I'll talk about later. So the modeling framework that we have starts from modeling the rainfall, and then the runoff, then hazards are formed over time and over space, flood and mud flow, landslides. Then we have the object events, which capture the impact on individual objects, for example, scouring in the bridges or inundation on the roads, and also the speed reduction and capacity reduction as functionality measures for our assets. And then we have network model, which puts together all these individual assets as form of a network. Societal events, which capture the impact on the society in terms of restoration and also traffic, how long it takes people to travel and how many times they cannot make their travel because some links are closed. And then translating all of them to costs, direct costs and indirect costs. So direct costs in our case include the costs of repair or restoration interventions, and indirect costs include the costs of additional travel time and also missed trips that could not be made, or opportunity costs, basically. And then we generate thousands of scenarios. So we have a probability distribution of the total costs, and based on that, we calculate the risk measure, which is the average for us, in this case, the average of total costs for all the scenarios we had. And then it comes to the stress testing or stress test assessment, which we have this underlying framework, but then a stress testing builds upon that. And then according with the underlying framework, we have multiple types of stress tests: source, hazard, object, network, and societal stress tests. So previously, I mean, the general opinion about a stress test before was that we design our system, for example, for a 100-year flood event, and then we stress test it using a 500-year flood event. But then in this work, we argued that not only the hazard should be stress tested, but all other parts of the system should be stress tested. And that's why we have stress testing in all aspects of our system. So each stress test changes some parts of our system. We introduce those changes to the system, and then we reevaluate risks, and then we see whether the new realization of risk is okay or not. This figure, just for the reference, shows an output of the simulation platform that we have, which shows the development of our system over time and over a space, where we have rainfall, when there is mud flow, in which area, in which time step, which assets are damaged, where the traffic flow is going, and all parts of basically the spatio-temporal representation of our system. So to just give some examples for stress tests, again, I refer to this general definition of a system, network, organization, and environment. So every part of that could be a subject of a stress test. For example, increase in the average intensity of rainfall events because of climate change, or increase in the travel demand. These two are the ones that I will talk about later and we modeled and evaluated. Or it could be that the number of work crews or contractors that we thought we would have to restore the assets are less than the planned, or they're not functional, for example. Assets are performing worse than design, so we have more damage than we expected, or lack of functionality of assets. This is also another common way of doing a stress test, that we remove assets from the network and then we evaluate the performance of the network without that asset being in place. So today I will show results related to two types of a stress test that we did. One on climate change stress test, which we used RCP scenarios, representative concentration pathways, which shows how much carbon dioxide is going to be trapped in our atmosphere. And we have four different scenarios: 2.6, 4.5, 6, and 8.5. And each one of them shows the percentage of increase in the temperature and consequently the percentage of increase in the rainfall, flooding, and all those climatic events. So Switzerland, similar to many countries, they have reports on the climate change projections. And if I draw your attention to the figure in the middle, it shows the frequency of precipitation, frequency versus precipitation intensity. The blue line is the current situation, and the red line is with the effect of climate change. And as you can see, the probability of higher intensity precipitation is going to increase in the future. That is exactly the concept of a stress test, that we have a new probability distribution for one of our variables. And then there are tables basically showing how the scenarios are going to unfold in the future, how it impacts rainfall in the future for the specific region of our case study. And then based on those tables, we picked three scenarios: RCP 2.5, 4.5, and 8.5. And each one of them says how much increase on average we have in the intensity of our rainfall events. So these are three stress tests or climate change stress tests. The next type of a stress test is increase in the travel demand. Switzerland, again, there is another report, Transport Outlook 2050, which shows how demand for different modes of transport is going to change in the future. For example, you can see here that there is going to be 11% more demand for passenger transport in Switzerland and by the year 2050. And then they have multiple scenarios, again, depending on how future unfolds, how much sustainable we are going to be, how much technology we are going to develop and adopt in our daily lives. And then based on that, they develop these tables that show how much passenger traffic for roads, or generally traffic for roads, is going to increase in the future. And again, based on these tables, we defined three scenarios. One leading to 4.6% increase in the travel demand, 18.4 and 22.7% increase. So we have now these six scenarios, and then one slide on the results. So these figures on the x-axis, it shows the increase in the increase in the intensity of the input variable. So one of them, the left side, is the rainfall intensity. The right one is travel demand, how much increase we have in these two variables. And on the y-axis, it shows increase in R, increase in the risk measure. So the black line shows the increase in the risk measure with respect to the increase in that variable. So for example, this is 11%, 10.96% increase in R if we have around 6% increase in the rainfall intensity. The red line shows the ratio between these two variables. So 10.96, for example, divided by 6. And then it shows for climate change, it is around 1.8, meaning that by 1% increase in the intensity of rainfall, we will have around 1.8% increase in risks. And for the travel demand, this value is less. So by 1% increase in the travel demand, or in the number of traveling vehicles, we have 1.3 to 1.37 increase in risks. And it shows how these two are compared, how we need to prioritize which parts of our system are more sensitive to these stressors, and how we need to allocate resources to mitigate these effects and reduce the risks. We can also do this analysis on one level deeper on different, for example, on direct costs and indirect costs separately. And it shows us which stress tests impact direct costs or indirect costs more, if it causes more damage or it causes more disruption to the network. And I will not talk about these numbers here, but if there's any question, I can explain. But basically, we can go deeper and see how each scenario of a stress test impacts different aspects of our system. And to wrap up, so we propose this simulation-based stress testing framework. But the next steps for us are, so we argue that every part of our system need to be stress tested. Then we end up having a large number of potential stress tests. And so the question is, which ones we need to prioritize and we select to conduct to have a good overview of the risk of our system. This is a topic of another research work of mine on prioritizing the stress tests. The next work is to set the thresholds for these stress tests and passing requirements, whether they pass or not. And if they fail, to plan for risk-reducing interventions to achieve satisfactory results, and eventually to develop a guideline on how to conduct a stress test for transport infrastructure that would help authorities and managers to set up stress tests, monitor them, and introduce the changes to their system to meet the risk objectives. These are some of the references that I used for my presentation today. And thanks so much for your attention.
Thank you so much, Hossein. I'd like to open up to the audience for questions.
I do have a question, unless someone else has a question first. So I am curious a little bit, and I know that over the years, Brian has had very close relationships with planning agencies and so on. And so a little bit, so for example, when stress tests were introduced to kind of look at the resilience of banks, this was after the recession in the early 2000s. They were very averse because basically these stress tests really they are extremely conservative, right? And so they require that basically policymakers, in the case of infrastructure, put aside like large amounts of money to kind of deal with these low probability scenarios that we are stress testing for. And so the question is, I'm curious what their reaction was if and when you presented results to them.
Yes, we have. We presented the results a few times, and we actually organized workshops on not simulation-based quantitative, but qualitative expert opinion-based stress tests. Because to build up these simulations, it takes a lot of time, years for a system, but we wanted to show in those workshops that it is useful, it can be set up relatively fast, relatively easy, and it could give some insights to the system. So the intake was good. It was we got a good feedback from the experts that we presented. It was experts from Netherlands, from Serbia, Switzerland, and we also did ones in Poland with some experts from Poland, from Slovakia, and Czech. And it all led to some further discussions for a real-world case study. In terms of the monetary budget to cope with the results, I'm not sure, but at least from the perspective of this being a useful tool, it was definitely positive.
Thank you. Are there other questions? Okay. Thank you very much, Hossein. And so I guess let's transition. And because Cal is wearing two hats today, he's both the moderator as well as a presenter. I will take over and actually present Cal. So Callahan Skiles is a fourth year PhD student at Northwestern in Transportation Systems Analysis and Planning. I have the privilege of working with Cal, and for the last I don't know, several months, he has really engaged in what is going to be his PhD topic, which basically is related to building a micro simulation model of intermodal yards. Okay, and so uh, just briefly, Cal has a bachelor's degree from the University of Illinois, and basically after spending a couple of years in industry, joined our PhD program. Um, I'm sure I'm forgetting many other things, but without further ado, let Cal take over and tell us a little bit about his work.
All right. Thank you, Pablo, for the very kind introduction. I am going to talk about a facility simulation for the majority of this presentation. This is a part of a larger project where a group at Northwestern and a group at Vanderbilt University are working together on freight decarbonization. So looking at the entire freight network of the US and looking at ways to make it more efficient and reduce its overall emissions. And so the name of the project is Imagined, with that standing for Intermodal Analytics for Green Infrastructure Network Energy Decarbonization. And as Professor Durango-Cohen mentioned, he is a part of this project, as well as Adrian and Basilis, who are on this call, and Professor Mamasani, also at Northwestern. So to get started, I am going to talk about the project kind of overall to give a little bit of background on it. Then I want to talk about multimodal facilities a little bit more to understand what these transfers are between modes, where they occur, what kind of facilities there are, and why we're focused on a specific one to start. Then we'll go into the simulation, talk about the model that has been built, and then go over a couple of scenarios and understanding how the model reacts to changing different inputs. All right. So project concept overall is there are two approaches to reducing the environmental impact of freight transportation. One is by utilizing advanced fuels and reducing the overall emissions and changing the type of energy being used for vehicles and equipment. So in the case of a multimodal transfer facility, this is looking at the cranes or the trucks that are moving the freight within the facility and looking at less emitting versions such as battery electric or hydrogen powered vehicles and equipment. And then the other way of reducing the environmental impact is by looking at shifting to more energy efficient modes. And when you're talking about that, these hubs of making transfers between modes become even more important because that is where you can make the most of these more efficient modes. So by utilizing the waterways or the rail network, you can use a more efficient mode for a large portion of a freight trip. And having these hubs be very efficient allows for those transfers to not have a negative effect to the point that it could not be used. All right. So this is the overall structure of the project. There is a building of the freight network, looking at energy infrastructure, facility simulation, and an overall logistics and routing optimization. And we're going to focus on Module B here and the simulation of a multimodal facility. So to kind of give a little bit of background of what we've done so far on the project, something that has influenced the existing simulation model significantly is we have met with a large number of stakeholders, including railroads, trucking companies, and ports. And through their very enlightening feedback and description of their operations. A lot of the statistics and inputs to the model came directly from these different stakeholders and how they actually operate within their facilities and what they're attempting to do by increasing efficiency and or reducing emissions. So the work we've made so far on the project has been looking at two separate corridors within the United States. One is a land-only corridor, so looking at surface transportation via truck and rail on the Los Angeles to Dallas corridor on the left. And then on the right, we have a corridor that also includes the Mississippi River to allow for three different modes, being truck, rail, and inland waterway. And when it comes to both of these, the multimodal facilities are what make the rail aspect of the corridor on the left possible as a multimodal corridor, because essentially everything that moves via rail has some sort of drayage or short haul truck trip on one or both ends of its journey. And so those transfers between truck to rail or rail to truck need to be well understood from an efficiency and environmental standpoint. And then similarly, that applies to this corridor, but you have the extension of transfers to and from the river. All right, so just to give a little understanding of outputs that have come about from these corridor analyses, we've got an analysis of the total emissions for different fuel types and breakdowns of the modes of transportation. So in this case, we have long haul truck and a combination of short haul truck and rail. And so to make this analysis even more realistic, we need to understand what's occurring at these transfer points. Because when you look at this right now, the short haul truck and rail has the much lower emissions, much lower fuel price, but without the time and the energy that is utilized at these transfer points, we're missing a piece of the puzzle. And then similarly, in the work that has been done by Facilis, who's on the call, on the other corridor, it's looking at how to optimally locate these transfer facilities on this corridor. And so with those optimal locations, we then need to understand what is actually occurring within those facilities and how we can make the most of those operations to have the most effective and efficient freight transportation network. So this flowchart is an encapsulation of what the facility simulation looks like in graphical form. And so what's really key from this is it shows how it isn't all about a specific mode or transfer between modes. The simulation we're presenting does most represent an intermodal rail facility, so transferring between train and truck. But a lot of the same processes can be simulated for going from a ship to truck or a ship to a train. And so when this shows the vessel arrival and then the unloading to a staging area and then moved by a hostler truck and then eventually leave the facility, that can apply in multiple different types of transfers. And then the other key point shown here is this refueling or recharging of the hostler trucks adds a layer of complexity and allows for some emphasis on reducing the emissions of the equipment involved in the operations. So to give some examples of these multimodal transfer facilities, just on the left, we have a list of types of them. So coastal ports, so the Port of LA and Long Beach, which is what's shown here, is a map of the terminals at the Port of LA and Long Beach, while also showing the rail connections within it. So all of these lines on the map are railroads, and the point here being that there are lots of on-dock and near-dock rail connections at these ports, and understanding the connections between the freight transfers from ship to train and ship to truck, how they differ, how they can be analyzed differently, what the efficiency differences are. There is a lot to look at within a multimodal transfer facility. When it comes to an inland port, the example I've given is in Joliet. It's the Centerpoint Intermodal Center, which is what we're going to talk about a lot because the current simulation model is based off of that. Some other examples are really any terminal along the inland waterway system is connecting the waterway to a surface transportation, whether that be a river port that's connecting just to truck or to train. And then you have intermodal rail yards located at other locations to connect to port facilities or major population centers. And then the last one is transloading facilities, which is often where freight is moved from one type of container to another. And that could involve uh, trains and or trucks. And what goes on there is oftentimes the containers that come off of the ships are international containers that are going to go back on the ships. And so the freight is transferred to a domestic container to move about the US. And understanding the necessity of those facilities and how they're utilized kind of as a mode itself from the port can really change the operations of the port. All right. So another key statistic that we're going to want to look at in understanding the operations within these facilities is dwell time. And so what's shown here is a daily report that the Port of LA puts out of how long import containers are dwelling at their terminals. And what you see here is the shortest one is 0 to 4 days. The shortest bucket they're keeping track of is 4 days or less. So that means that under 4 days is thought of as a somewhat reasonable amount of time to have something sit in the port, which it is in this case. But when you're thinking about uh, improving efficiency, what is the easiest way to do so? One could be to reduce dwell times to a point lower than where they are currently. And so maybe if the average went from 5 days or 4 days to 3 days, how much more efficient could the operations become? What is the change in throughput? What are we able to do from an efficiency standpoint by reducing dwell time? And then in a similar vein, this is a graphic put out by J.B. Hunt to compare the different types of intermodal services. And I found it super interesting because it shows somewhat their bias in the transload facility, because that is the part that involves more trucking. And so the transload facility means that it needs to get to the transload facility from the ship, and then a truck is involved in that process. Then it goes on a train, and then a truck picks it up at the end. Whereas the inland port intermodal or international intermodal gets directly off of the ship and can be put directly on the train from the port and shipped the same distance. And which of these is more efficient is up for debate within the freight world, depending on who you talk to. But what you can see here is by having this additional step of the container going from the port to a transload facility, transloaded to a different type of container, and then put on a train, it's interesting to think about that as being thought of as more efficient than something staying in the same container, being directly put on rail and shipped the entire way by rail, and then picked up by a truck at the end. And so this handling of international containers is something that we have been thinking about in the intermodal rail simulation, and whether other facilities could add it as a functionality to their current functionality as a domestic intermodal transfer facility. All right. One other type is the idea of container on barge. And so this is containers coming to the country via ocean vessels and then transferring them to smaller vessels that can go in the inland waterway system. This is a current plan for a facility in New Orleans where large ships could come and smaller ships could come. And what this shows is the ability to transfer containers from one to the other. And then the smaller ship could go up the river and allow for a new market of containers moving within the country. This is an example of a river vessel for containers. All right. Now this is what the simulation is based on exactly, is these two intermodal rail yards that are right near each other outside of Chicago. And they have a lot of different types of functionality. They have these electrified, and some of them are automated wide span gantry cranes that can unload multiple trains at once. And they also have diesel powered cranes that, or more like trucks, in that they have rubber tires and pick up a container and drive it away. And so from that intermodal rail yard in Joliet, where they handle a lot of international intermodal containers that are unloaded directly there and taken away by trucks almost exclusively. We've set up a MATLAB Simulink simulation model with a number of subsystems to capture the arrival of trains, the unloading of containers, the containers then being moved by Hostler trucks from the area of unloading by the cranes to an area where external trucks have picked them up, and then the pickup by external trucks. And then this is a short video, just a screen recording of how it runs. And so one of the reasons we chose this MATLAB Simulink software is it is graphically digestible, is how I've been phrasing it, is you look at it, you see how it flows, you can watch how the entities flow through it, and you can see how things are related in these connections between subsystems. So that was just a snippet of it running. All right. And then if you want to break into those subsystems, we can go a little deeper. The first one shown here at the top was a crucial part of the model first working. It's the Hostler charging subsystem. And so the user input within this subsystem is a mean charging time. And the way this is set up is it sets for an exponential distribution for the charging time. And this allows for the hostlers to be generated as entities. And then when they flow through the system and they have enough charge or enough fuel, they enter the rest of the simulation so that they can pick up more containers. But if they don't have enough fuel or battery level, they get sent into the charging queue and need to charge. And so we'll talk a little bit more about the impact of this charging time on the operations. And then the other subsystem that is the most novel or the most interesting is this Hostler container move subsystem. And what's interesting about it is it is the subsystem within the model, when you look here, that connects the two types of entities. So in Simulink, the standard entity is like the thing that is moving through the simulation. And so in this, you would think of the containers as the primary entity, because that is the freight that is moving through the system. But to have the hostlers have some level of agency or functionality, they are also generated as entities and then combine with the containers at this point within the subsystem, and then are moved by a server that acts as if the hostler is serving the container. And this then moves on and leads to the hostler dropping off the container in a separate area. Yes. Okay. So just to give an idea of what the current variable inputs are within this model, I'm not going to go through all of these, but I wanted to show that in the scenarios I'm about to present, all of these inputs are fixed except the mean service time for charging. So I used that one to show the impact of charging time on the model flow or just operations. And everything else is fixed. So a train arrives every 4 hours. There's 300 containers per train. The cranes operate every 3 minutes. And every one of these values is either based on a figure we were given by the railroads for their intermodal yards, or is based on information from a electric truck manufacturer or operator. So, and so to get to that, the model scenarios, in this output, this is when the Hostler charging time is 45 minutes. That's the mean charging time exponentially distributed. And so this graph on the left is how long a Hostler has to wait to charge on at that point in time. And so what you see here is at a point, once operations have gotten going, it spikes very high because the hostlers have all been operating essentially at the same time while containers are being unloaded to start, and they all start with a full battery. And so it spikes to this over an hour of wait time and then levels out to kind of a approximate 10 minutes of wait time. And the graph on the right is what I've been using to understand the steady state of the simulation. And so this is where the cranes unload to and the hostlers pick up from. And so this has a lot of sensitivity to the changing of variable inputs. And when it levels out and does not hit the max of 300 and does not stay at 0, it shows that the simulation has hit a kind of steady state. And so now what we're going to show is when the charging time goes up to 75 minutes on average and drops to 15 minutes on average, and nothing else changes. So at 75 minutes, the graphs look very similar in structure. So the difference here is now it spikes to about 85 minutes early in the simulation, but then it levels out around 20 minutes at this point in time. So this runs for 100 hours of real-time simulation, and that shows a key difference. And then the staging spaces, it's also not leveling out quite as much and also at a higher total value. It is slight, but it does show the slight difference in increasing the charging time by 30 minutes on average. And then to see a very different graph, when you look at the 15-minute average charging time, it has drastically changed. And so this is LB for not changing the scales properly. This only goes up to 4 minutes. So this is essentially saying once that initial rush is over, you don't wait for a charger if the charging time is only 15 minutes on average. And with no other characteristic of the model changing, the Hostler charging time being 15 minutes means that we don't ever even fill 50 of these 300 available staging area spaces. And so there's a lot of different types of outputs that can be made from the model, lots of different inputs that can be changed to see how they impact the outputs. And I wanted to use this example to show how it responds to one specific one that is very important and very variable. Like the amount of time it would take to charge a Hostler depends on the fuel type, depends on the type of charger, like the level of charger or the amount of electricity available. And so there is a lot to be seen here. And so just a couple of the extensions that we're currently working on. One is a multiple process path unloading. And so I mentioned quickly that the facilities we visited had wide span unloading where they unload multiple trains at once, and reach stackers, which are more like rubber tired trucks that unload containers from trains. And we wanted to be able to manage the flow to each of these and see how that impacted the efficiency of the facility. Another one is working on the reverse flow. And so now the hostlers are not only picking up full containers and moving them through, they are picking up empty or outbound containers and moving them back through the facility so that the cranes will be able to load them onto trains. This is making it more realistic for what occurs within the facilities. And then what I wanted to do is just go over a couple different sets of operational questions, but they're more just to get people thinking. These are specific to the model that is built and understanding what kind of upgrades the facility you would want, how you would implement charging stations, and as I mentioned, the split of flow between the different unloading processes. And then the other was one that I was just sort of working on, was trying to understand the other types of facilities that could be modeled similarly and how we want to think about them and what questions we could potentially answer for those types of facilities. And that is the end of my presentation. Thank you all for listening, and I would love any feedback or any other ideas for what to specifically look at.
I have a quick question. If I mean, thanks, Cal, for your presentation. Um, just have a general question for one of your slides that you showed, slide 11, on which way is more efficient, whether we have all by train or one like halfway with the truck and then some with the train, if I'm not wrong.
Probably on me.
So,
Count them right.
or the one that was JB Hunt, something like that, I
Oh,
guess.
yeah. Okay.
I don't know if maybe the number that I wrote down is not
No,
correct.
you're right.
Yes, this one.
Yep.
I mean, based on the numbers on the right, it seems that the one the transload way is more efficient. Um, but you mentioned that it's still debatable, and some probably do not agree. I was wondering why or how.
Yeah.
Like, I mean, based on these numbers, it seems to me clear that the
Yeah.
transload version is more efficient.
That is what they want you to think. Not to be
Mhm.
cynical. Uh, this is the process that JB Hunt wants you to pick because it involves a lot more trucking, and it involves a transloading facility that they either would operate or would be heavily involved in. And so the key difference here is they're saying that when these containers arrive at the port, they are getting them to the transload facility immediately rather than it's sitting in the port 1 to 7 days. And so it sits in that transload facility for 2 to 3 days. And so if this goes back to my point about the dwell times within the ports, if this dropped to 1 to 3 and this was 2 to 3, now this would be a wash on what's going on there. The days spent on train is approximately the same. They add an extra here because these international containers usually have lower value freight, and so the railroads don't prioritize them as much.
Mhm.
And then this one at the end is also kind of uh, biased. Is days to delivery from ramp is a railroad or trucking term for these intermodal facilities. And in the priority domestic freight world, it is more likely that it takes 1 to 2 days, whereas in this lower value international freight world, there is not as much of a rush. And so oftentimes things do dwell at these
Mhm.
international intermodal facilities for a week. And so these numbers aren't fixed. They aren't like innate qualities of the process. They're how it works because it usually involves lower values versus higher values. Um, and that's something that or I have been looking at and I find extremely interesting because to me, it seems like keeping something in the same container and keeping something on the railroad as long as possible, like without transferring to truck at the beginning, has more efficiency to it.
Efficiency in what measures, Cal?
Yeah. So what's not shown in this graphic, and I might be talking in circles a little bit here, is
No, you did great.
how things get from the ship to this transload facility is it goes in the port and then has to get unloaded from the ship to the dock and then has to get picked up by a truck and a truck takes it to this transload facility. And so that time is not built in here. Then at the transload facility, this 2 to 3 days, the freight is transferred from an international container to a domestic container. And that process, the process of getting it from the ship to the dock, and then the dock to the transload facility, and then what happens within the transload facility, those two steps, dock to transload and what happens within the transload facility, seem inefficient compared to a container being directly put on the railroad at the port and getting away as far as it needs to go on rail.
So what I was thinking is, so you've described travel times, and so in addition to travel times, of course, like the above mode is both cheaper and also more energy efficient than going by truck. And so, but of course, it's exactly what you said. What the trucking company is selling you is their competitive advantage, which is travel time, shorter travel time.
And more defined, right? Like less variable. It's more likely to be exactly 9 days in this situation than it is in this situation.
Yeah.
Thanks.
Yeah. So thanks. Unless there are other questions, I think that we can end our session for today. I don't know if Bob has any comments or questions. So yeah, so with that, thank you. This is the end of our sessions for the fall, and we are well on our way to basically filling the sessions for the spring, which would be a lot of fun. Thank you, Hossein, for your presentation. Thank you, Cal, for your presentation. And yeah, hope everyone is doing well.
Yeah, happy holidays, and
Yeah, thank you.
Thank
you.
Thank you.
Thanks. Thanks, Cal. Thanks, Adrian.
Thank you, Cal.
Thanks.
Yeah. Thank you, Hossein.